are joining us from the Internet 2 office in Washington, D.C. We ask them to join us based in part by information provided by our new Vice President for Research, Mike Zani, and also information presented from the I2 organization about work the agencies are involved with related to cyber infrastructure. The panelists have agreed to provide you with information on how cyber infrastructure will affect their current and future RFPs, including technological expectations the agencies have for researchers and their groups. We've asked them to speak for 5 minutes or so, although we have enough time that I think some of them may want to speak a little bit longer, but then we're hoping to have a discussion. So I hope you folks will be thinking about questions, because this particular session is intended to be interactive. The people that we have, I'll go down the list, if you could raise your hand. Guy Alms. Guy? Thank you. He is a program officer in the Office of Cyber Infrastructure at the National Science Foundation. He oversees a number of activities, including some related to the extensible terrace-scale facility. While at NSF, Dr. Alms is a rotator whose home institution is the Internet 2 project, where he serves as chief engineer. Peter Hyman. Is currently senior advisor to the director of the National Center for Research Resources at NIH. Before joining NIH, he spent 4 years as a program manager at DARPA. He worked for 11 years at Schlumberger and was also director of a successful medical software startup. His PhD is in computer science from Carnegie Mellon University. Mary Ann Scott from DOE. She is a program manager in the Mathematical Information and Computational Sciences Division of the Office of Advanced Scientific Computing and Research. For the past 8 years, she's managed a program of research and development for collaborative technologies that scientists and engineers need to access remote resources and facilities, and to collaborate effectively as members of multidisciplinary distributed teams. Finally, Sengar Lee. He currently manages the NASA high-end computing portfolio. He previously held positions as Senior Technical Advisor at Northrop Grumman Information Technology and Research Scientist with SAIC. He graduated from Colorado State, where he got his PhD in Atmospheric Science and a Master's in Civil Engineering. So I'm going to turn it over to the folks in Washington, let them say what they ever want to say, then we'll go ahead and have some discussion. Okay.
So thank you, Charlie. I think the list says that I go first, so let me try. First of all, I'm very glad to be speaking with you. About once a week, I come down on the Amtrak from the New York City area to Washington, D.C., and go by Rutgers and wonder what goes on there. So it would have been even more fun to be there in person, but here we are. I want to say a few things. First of all, to preface it, I think that NSF has an ongoing deep interest in the nature of the university as an institution and the success that university people have in their teaching and their research. Because of the teaching mission of the university, it seems like every discipline has 1 or 2 people on campus that are needed for the teaching mission. And then when those same people shift gears to do their research, they find that the people who share their passion for the research niche are scattered all over the country and in fact all over the world. And that makes us disproportionately dependent on technologies and infrastructure and ideas that support collaboration. So effective collaborative research, effective access to resources around the world has been an important thing for university people for many years. And so enabling that collaborative work is an important thing for the foundation. My little part of the National Science Foundation is called the Office of Cyber Infrastructure. It's only a few months old, being formed in July of 2005. Originally, back 20 years ago, when I first met Charlie Hedrick, there was a thing called the Office of Advanced Scientific Computing at NSF. And that managed both the NSFNet project and the early NSF Supercomputer Center work. And then beginning in the late 1980s and until about a year ago, all of that activity was put within the computer science directorate called SCIENCE. And so in a sense, we're sort of back to the way things were 20 years ago. Dan Atkins, a rotator from the University of Michigan, will be joining us in June as the first permanent director of the Office of Cyber Infrastructure. And we're looking forward to his leadership very much. But a couple of other things, that is that cyber infrastructure at the foundation is much broader than simply the activities within our little office. For example, to show an indication of the importance attached to cyber infrastructure, there's a thing called the Cyber Infrastructure Council, whose chair is the director of the NSF, and whose members are the assistant directors for the very large directorates within the foundation. This is a very, very high-level management committee. When I first heard about it, my expectation was that they would meet about once or twice per year, and their lieutenants would meet once a month or something. But on the contrary, those people meet about once a week. They're very interested in crafting cyber infrastructure projects within the NSF, including the work in OCI and in the rest of the foundation. The word cyber infrastructure is a relatively recent coinage that describes things that have been going on at NSF really for the last 20 years with varying degrees of explicitness. So for example, going back to the mid-1980s, you have advanced computing. The original 5 NSF supercomputer centers, including at Princeton and at Cornell, at Illinois, NCSA, and San Diego and Pittsburgh, were contributing at that time. And today, NCSA, Pittsburgh, and San Diego are still the three largest components of the terror grid. And their computing facilities can continue to increase in not only in size and capability, but also in diversity. It's also the case that we're beginning to take a look at advanced instruments as the first class part of cyber infrastructure. For example, online access to astronomical telescopes, to sensors, radars for weather research. There's a thing called the spallation neutron source at Oak Ridge, which we're going to attempt to make an online instrument that's part of the terror grid. Advanced networks are very important. It's important to realize that at the same time the supercomputer centers got started, the NSF project got started, which connected, in the end, all of the research universities to the internet. And so networking, instruments, and computing remain important strengths of cyber infrastructure. One that's come relatively recently is software. You'll hear this phrase, middleware, to describe the particular kinds of software that enable collaboration to be done successfully, securely, etc. And putting all of these things together in a synergistic way really comprises cyber infrastructure. One of the examples I like to point to sometimes for how this can be done in the future is a thing called the CRAFT project from the University of Oklahoma, where they aspire to be able to develop the technology for predicting tornadoes with very high reliability, say 3 hours in advance. This kind of thing is shown to be important, for example, by the tragic storms from Sunday night. That's a good example of the effective application of cyber infrastructure, and it's increasingly successful. In this case, you have about 150 Doppler weather radars scattered around the country that are effectively accessible in real time and provide real-time data as inputs to weather models running at supercomputers. For example, during the springtime, these scientists have access to the supercomputer at Pittsburgh Supercomputing Center and are able to run real-time analyses of things, and have become quite successful at anticipating these storms. And then, of course, you need networks to allow that data to reach the supercomputers in real time, and advanced software to make it all plug together. That's an example, one example from weather sciences that is just one inkling of something we'd like to become more common, more prevalent. Current projects within the office include core support for the historic Aggie centers at NCSA in San Diego. A recent thing called the Sensible Terascale facility, which is most often called the terror grid. The most visible networking project is a thing called the International Research Networks Connections program, which supports the high-speed connectivity of networks in the United States to corresponding high-speed networks in Europe, Asia, and increasingly to Latin America as well. There's also a thing called the NSF Middleware Initiative, which provides core support for a lot of software that, for example, the Globus software packages, the Shibboleth software packages for security, a number of other things that make grid computing viable activity. At the human resources area, we have a project called CI Team, which is a bundle of education, outreach, and training facilities that take the understanding that all of this cyberinfrastructure resource stuff is not useful at all unless we cultivate students, faculty, etc., who are able to make full use of it. Most recently, we have a set of high-performance computing acquisitions. There were a series of proposals we received in mid-February that we're working on right now, should be awarded late this summer, and that's a $30 million program. And that's our small HPC program. There's a larger set of activities planned for later this year, which is the beginning of a set of activities that should lead to petaflops systems by the end of this decade. A few words about the TeraGrid. It's a distributed system of very large scale. On my slide I said more than 90 teraflops total, but I'm advised that it can now reach 100. We have 8 different resource providers, including at San Diego, at NCSA, Argonne Labs near Chicago, Purdue University and Indiana University, Oak Ridge, also the Texas Advanced Computing Center at UT Austin, and the Pittsburgh Supercomputing Center. Those 8 resource providers operate a diversity of data collections, a diversity of supercomputers, integrated with each other with both the high-speed networks and high-speed and advanced middleware, and integrated operations. So this is both a powerful set of resources in itself, is also a structure into which future NSF investments in new resources can be more effectively integrated. Very soon now, you'll be able to see on the NSF webpage the thing called the vision document for cyber infrastructure that's been built over the last several months by a variety of people, really from all the directorates of NSF. This is by no means a document just from our Office of Cyber Infrastructure, but rather a document that reflects the vision for cyber infrastructure by directorates that include the biological sciences, the geological sciences, mathematical sciences, engineering, and others. So a very broadly assembled crew of people put together this document. We're going to have chapters in high-performance computing, chapters on data, chapters on collaboration and communication support, and a chapter on education and workforce development. It should be out in its draft form during the first part of this month. So I think I'll stop there and pass the time to my colleague. Peter?
I'm one of those 4+ souls who doesn't have that PowerPoint up and therefore flounder hopelessly, so just bear with me. First, a little bit of a disclaimer. So I'm here from the NIH. My views are largely personal, and as we get into the Q&A, represent personal opinions, not those of the NIH. So with that behind us, what I'm going to do is very quickly give you some examples and guidance of things that are going on that probably a good number of you who work in the biomedical research field are already aware, and I hope some that you may not be aware of. So first, just looking around, there's already a trend for research to be informatics-supported collaboration across disciplines, institutions, and geography. We see that within the NIH, and I'm sure everybody else sees the same thing. Now, the examples I'm going to give are some very tight plays on supercomputing and networking, the normal things, and also some specific examples of projects that can reach across this space into perhaps more in line with this observation of the way things are going. So, first observation, if you look in the National Coordination Office for IT R&D, you will see that the NIH invests one of the larger amounts in information technology research and development, I think behind the NSF, as reported in R&D. The NIH is already a significant player in informatics research and development. If you look at the NIH, in science, not, again, you're not in the biomedical research area, we're a little confusing, perhaps. We're actually 27 separate institutes and centers, of whom there are some very large ones like cancer, infectious disease, heart, lung, and blood, and of course the National Library of Medicine, which is probably best known to those folks who work in the informatics area. Straight supercomputing play. There's several examples around. One I happen to be most familiar with is called MIDAS. This is where we're modeling the spread of infectious disease, one in particular at the moment, and to do those models, very large agent-based models, particularly for North America, there are a number of research groups working inside MIDAS independently. And as of the fall of last year, we've been making pretty heavy use of NSF-supported resources at NCSA, and now we have a number of terabyte allocations. That's the scale that's needed, the scale of computing that's needed to do that kind of work in a timely manner. Looking at networks, it's probably not well known that some parts of the NIH support physical network build-outs. So we have the Lariat program run by Dr. Mike Sayre, and that's been addressing networking needs, physical networking needs in the northwestern states. These are so-called idea states, states that traditionally been underfunded or haven't received what you might expect to be their portion and share of grants. Just part of that issue might well be infrastructure. So Larry addresses that. One of the high points of the demonstrations a little over a year ago was to stream 600 megabits per second from an electron microscope in San Diego to a meeting room in Hawaii. And that was done mainly. A key piece of that, not all of it by any means, was supported by the Lariat program. There will be a meeting co-organized by Internet2, the National Center for Research Resources at the NIH, and TATRIC, the telehealth group in the Department of Defense, on connectivity at the start of the Internet2 meeting this year here in DC, looking for direction. Now, so for us, then there's informatics, which is the way the biomedical world usually refers to information technology, but that incorporates less of the keep the mail working as much as the bioinformatics, all the tools that we use routinely now, like databases, all the systems that we have. In terms of collaboratories based in that space, I'll point to two. First is a significant investment by the National Cancer Institute called CA-BIG, the Cancer Bioinformatics in Grid, Biomedical Information Grid, actually close to that, CA-BIG, which is providing an awful lot of middleware across all the cancer centers. In the National Center for Research Resources, we have the Biomedical Informatics Research Network, the BURN, which at this point is connecting about 23 major sites, several hundred researchers. And both of these aim to support this notion of making data available, findable, in different forms from wherever you are, with security, all the other things that you would expect in place. Next, the NIH has a number of activities that go across all the institutes and centers. These are called our roadmap activities. These are started by the current director, Dr. Zahuni. Two I'm going to mention. First is the National Centers for Biomedical Computing, which address head-on the notion of bringing more computation, in this context of this session, perhaps cyber infrastructure, into common play in biomedical research. We can talk about those in the Q&A. And one you're probably not aware of that has informatics as a component of it are the new Clinical and Translational Science Awards. The first round of these, the applications have just been received, and these are clinically oriented, clinical and translational work-oriented activities which have a called out informatic components. There are a number of challenges to be faced introducing heavy computational component of cyberinfrastructure angle into this space. As many of you are probably aware, a lot of that is cultural, just changing the way you do business. And there are a number of others that, again, we could get into. Some are straight access to structure, privacy, security, while keeping research going. Curation for the long term. Generating all this data, where do you put it? How do you keep it? Questions like that. So, any of my observations that there doesn't appear to be a trend towards research as informatics supported collaboration across disciplines, institutions, and geography, and we're seeing it, and I think we're going with it. Again, personal observations given by somebody from the NIH, not representing the NIH.
If we follow the introductory order, I guess I'm next. I'm with the Department of Energy, and I'm in the Office of Science, which is one of the many offices within DOE. The Office of Science is very much like NSF in that we do some basic research as well as more applied research. But unlike NSF, we're very mission-oriented. DOE has its specific missions related to energy, the environment, etc. Within the Office of Science, the Advanced Scientific Computing Research is concerned with supporting those missions and the other offices within the Office of Science that conduct research in biological sciences, environmental sciences, fusion science, basic energy sciences, combustion, and things of that sort, as well as conducting our own research in applied mathematics and computer science. So to set the context, in addition to the research, we have the facilities that you need to be able to conduct this kind of work. These are computing resources and networking resources. Within the computing side, we have an organization that's been around for a long time. It's called NERSC. It's located at Argonne National Laboratory, and it provides high-end capacity computing to the entire DOE SC research community. And when I say the entire DOE SC research community, that includes all of our laboratories. The department has, I think the total, I've forgotten exactly what the total is. There are 8 within the Office of Science and 3 in the defense side of the house. But we also sponsor research at universities such as your own. And this means that the Office of Science is very much a distributed enterprise with institutions we serve located from the West Coast to the East Coast, Midwest, the whole shebang. So NERSC provides computing resources for that community. And they currently are running a couple of machines that provide on the order of 12 or 13 terabytes. But we have plans to upgrade that to a peak capacity in the range of 150 teraflops by the end of 2007, fiscal year 2007. So this is our workhorse. Medium to very large projects need such capability, and they can find it there. We serve a number of large projects, 200 to 300. In addition, we have this need to support the very high-end computing needs of the scientific community within the U.S. And we do that through leadership class computing facilities. Our leadership class computing facility at the moment is located at Argonne National Laboratory, Tennessee. It has two machines, both Cray type machines, the XT1, for example. And it's devoted to a number of smaller projects on the order of 10 to 20. And we plan to upgrade that facility to more than 250 teraflops by the end of 2007 and up to a petabyte by 2008. The second plan that we have in the leadership class is to acquire a 100 teraflop blue gene feed to be located at Argonne National Lab in fiscal 2007 and increase that to somewhere between 250 and 500 teraflops by the end of fiscal year 2008. Hooking all these things together, we have our Energy Sciences Network that's been around since the 80s, mid-80s, mid to late 80s. And we currently have a backbone ring that encircles the entire U.S. That's 10 gigabits per second in the northern route and 2.5 gigabits per second in the southern route. Our plan there is to evolve this to 40 gigabits per second rings, two of these, with fault tolerant 10 gigabits per second connections to most of the SC labs, which will give that kind of capability to interface with the computing centers that are located in those laboratories. So that's where we stand with our facilities. The research that we do covers applied mathematics and computer science, and it's focused on delivering the operating systems, the programming models, software tools, mathematical algorithms, and libraries that scientists need to be able to make effective use of petascale computing. One dimension that we've expanded this research into is called scientific discovery through advanced computing, SciDAC. SciDAC started about 5 years ago, and it's focused on creating a comprehensive scientific computing software infrastructure that's fully integrated, applied mathematics, computer science, and computational science, the physical sciences, the biological sciences, and the environmental sciences. So the key here is multidisciplinary, very high-end, solving problems that you can't solve just within one small group or one small discipline. You have to have the interaction between the computer scientists and the mathematicians developing the algorithms and the scientists who understand where they need to take their science. Another dimension to this is that these very large simulations that you're wanting to do, maybe it's in astrophysics, maybe it's in accelerator design, are going to generate a lot of data. So the extra dimension there is data management and knowledge discovery, tools for data-intensive science. This may be for the simulation, but it also may be for the experiments, the facilities that we have. Guy has already mentioned the Spallation neutron source at Oak Ridge. So that's one source of data that we are going to make available. SciDAC, as I pointed out, has been running for 5 years. We're in the process of recompeting that program. So the timing is not quite right for you here. We have proposals in, and over the next 2 weeks, we're going to be evaluating those and putting new projects in place. But it's also probably going to have some expansion in some years down the road. So this data management dimension is certainly important to that program. It includes a distributed science software element to it. And this is focused on supporting this distributed data management through gigabit networks and services to interconnect the data analysis and management centers that are associated with the petascale computer and with the experiments that are generating these massive data sets. The research efforts are also focused to accelerate the development of approaches for operational cybersecurity, something that's becoming really very, very important, and evolving more and more in that direction every day. And it's also focused to develop and deploy distributed, scalable authentication and authorization schemes. High-performance middleware, also mentioned by my colleagues, needs to consider, in our case, things like network caching and computing, as well as fault tolerance and error handling. And since we're going across domains between the laboratories and the university research environments, those interface issues are important to being sure that we can handle and get the right kind of end-to-end performance between a scientist and whatever system he has to be working with on the other end. Just a couple of things about, this is what we're talking about for the future, what we've done in the past, primarily through the SciDAC program. Those projects are ending in June. An example would be the climate community. What we did there was develop a secure portal to serve up data that's being generated by the International Panel on Climate Control, IPCC. We have two archives located, one in NCAR, and here this goes across both the NSF community and the DOE community doing climate research. The data that's being generated by all of these models is made available through this portal. The archive is located at two different locations. And it makes it very easy for a climate researcher at some university location to find specific data and pull that down with very, very little effort. This is a tremendous change over what was in place 5 years ago, when first of all you had to figure out who it was who might have generated this data source, this data set that you needed to look at. Where is this person? Get a hold of the person, then the person has to find the data, and maybe in a couple of weeks later you could have it in your hand and analyze it. So I'll end with that example of what we think to be a very good success story of some of the work that we've been able to do to this point. Thank you.
All right, I guess I'm next. I'm from NASA in the Science Mission Directorate, specifically in the Earth Science Division, Earth Science Research Division. And within NASA, because of our Earth Science uses the most computing type computing and networking facility, and also we generate lots of data. So NASA's management decided that Earth Science will be managing the high-performance computing and networking infrastructure for look at the science mission's strategic plan, we focus on three things: data, modeling, and decision support system. We want to do the observation, which generate data, and use those observations, use those data to constrain our model, and use the model and data to constrain and to tie into the decision support system, which has the implication, a lot of the implication in policy, management, and decision. In order to support that framework, of course, high performance computing and networking is absolutely essential. So we have this scientific computing portfolio, which is basically supporting that kind of the infrastructure that supports the research. Of course, we also support the engineering decisions. For example, we have the shuttle analysis that's running on our high-performance computers, and also right now we are developing new crew exploration vehicles and large launch vehicles. So we are doing a lot of the analysis, design and analysis for that kind of new capability. Right. So the high-performance computing, networking, storage, data system are all very, very important in our mission, and we support this kind of infrastructure. And also we have already developed a number of research programs, and we are in the process of developing more collaborative research in our different missions. I want to talk a little bit about the networking and data system. Many people here talk about networking, mostly talking about networking on the ground. In NASA's context, when we talk about networking, mostly is going up to the deep space. And when we say ground network is pretty much antennas, and how do we connect, how do we receive the data and send it to our data center. So a lot of times, when NASA people talk about networking, it's really going up. But of course, at the same time, we need to send the data from our antennas to the archives. So NASA developed our networking infrastructure to carry those data flow. We are in the process of upgrading the high-speed network to support our data and computing requirements. In terms of data storage, we are generating just the Earth observation satellites. We are generating about 3 terabytes of data every day, and we are currently holding about 3 or 4 petabytes of data in our US disk system. On the modeling side, we are also generating multiple terabytes, about 2.5 terabytes of data a day, and most of the data are stored in our modeling archive, which is now currently about 3 petabytes also. Now, a lot of interest is in how do we manage the data, and how do we extract information from that large volume data. So we have a number of research projects that's focused on data management, data mining, and data fusion. And a number of project programs like Access, Reason, Advanced Information System Technology, Advanced Information System Research, are all supporting that kind of project. In terms of facility, I haven't talked about all the projects, but the facility itself, we have 2 supercomputing centers, one on the East Coast at Goddard Space Flight Center, and one on the West Coast at NASA Ames Research Center. Ames Supercomputing Center has one of the largest supercomputer currently operational, fully operational. Project Columbia is a 60 teraflop facility, 10,000 processors. And within that 10,000 processors, we have 4 512 clusters, cluster nodes connect together and provide a tightly coupled cluster for large-scale simulation. And we use some of that cycles to support National Leadership Computing System. We just made a call a couple months ago and just finished. We have made a selection. 4 projects come to our Ames Computing Center. Some of them received 1 million processor hours. I think the biggest one received about 1.8 or 2 million processor hours. So those are the large-scale simulation projects that's currently running on Ames Research Center machine. On the East Coast, the Goddard Space Flight Center is focused on Earth and Sun space science research. And one of the projects that's coming online, we call it Modern Era Reanalysis Project, which is basically analyzing all the satellite and in situ observations for the atmosphere past 30 years, put together a large-scale reanalysis data set. We are going to put it online, 400 terabytes of data online, fully accessible by the research community. And we are developing web services for people to access data anywhere in the world. So I pretty much touched every single area. One thing that we are doing also with collaboration with DOE and DOD called Data Intensive Computing Environment, DICE, which is the concept itself is pretty much similar to the TerraGrid, but it's on a smaller scale, rapid prototype, kind of putting together the analysis node with the loss of data behind those front-end environment. So we have access to those data in real time and do the analysis in a distributed sense. So that's where we are going.
Thank you very much. me start by asking whether there are any people at any of the sites that have questions. I certainly hope there might be. Anybody? Okay. I'll repeat the question because we're not sure that the roving mic is tied into the meeting system.
We have a question in Newark.
Okay. Go ahead.
Okay. First of all, I want to say thank you very much for coming to talk to us. It's really exciting to have an opportunity to talk to folks in granting agencies about what's going on nationally. I particularly appreciated, Marianne, when you talked about the idea of multidisciplinary, high-end collaborative research. I'm teaching right now in the IT and informatics program here at Rutgers, and I'm wondering if you could, any of you could give us some direct hints or tips for submitting successful proposals, particularly in the areas of life sciences, chemistry, and engineering.
Okay, I guess I'll see what I can say about this. First of all, you have to get the science right. And second of all, the multidisciplinary approach is becoming more and more important. And it's also important to have real partnerships. If you're doing something that is in the computing arena, having the right kind of ties between the computer scientists and the scientists who are doing the work is an important thing to do.
I might chime in and add to that. Many times when it comes to multidisciplinary research, I've seen it many times in the review panel discussion. A lot of times, because of the team that you have to put together and the resource required to support that team and support the multidisciplinary research. A lot of comments from the community is it's better to put together a team that responds to a priority that's set by the community. And so if you are doing something that easily that's supported by the community, the whole community, and this is a happy priority thing with a lot of resource requirement that's going to be better received by the review panel. Hope that's helpful.
We had a question in the room.
I have a question for Mr. Lee. Could you repeat the name of the project at the Goddard Space Studies Institute and tell us who the users might be?
Did you hear the question? This was for Dr. Lee. Could you repeat the investigators involved in the project at Goddard? You said?
The name of the project at the Goddard
The name of the project
Space
at
Institute.
Goddard. Tell us a little more about it. Are we getting through?
Question for Mr. Lee.
I think we lost Washington.
There we go. Okay. How much for pretty?
The project itself is called Modern Era Analysis Project. It's geared toward putting together the reanalysis data, atmospheric reanalysis data for the past 30 years.
And who might his users be?
Who would the users be?
Okay, right now we have a users group comprised of weather and climate research community, some of the community members. And once the data is online, we anticipate to have a lot more, we anticipate to have calls for additional university research come in to use and analyze those data. And that will be most likely in 2007.
Another question back there?
I guess it is a question to all speakers. I just want to mention that both Department of Energy and NASA have very big databases, and PCMDI did a very good job with collecting IPCC data for last report. But university scientists, especially in geophysics and I guess in other directions as well, the problem with sorting the data and collecting the data at the site. So we can access the central databases, but so local databases are becoming very large, and I believe that at this time computer power is enough to produce more data, and so they really need the problem with managing this data on site. And when we retrieve data from central databases, usually so many scientists have the same databases, and this does not help to save the space. Is any plan to support the how to say the data banks on site at the university levels? Because I think so it will be very soon. So they are limiting factor for research.
Were you able to catch his comments, or do I need to repeat this?
No, we can't hear that, guys.
Okay, let me
turn off your speakers.
All right, let me see if I can get at least some of it. This is a question for all speakers, and is coming from an engineering perspective. They're dealing with, as everybody else, increasingly large amounts of data. They have, local databases are getting large. It raises issues of how to manage data. Also, they find that when they access data elsewhere, many centers tend to have the same amounts, the same data. He wonders whether there is some intention to support data and data management, I guess, at universities.
Right. Maybe this is better as a dialogue rather than just a straight answer, because it's a big issue. I think that essentially every aspect of cyberinfrastructure supported science is becoming increasingly data intensive.
Yeah.
You're just going around the panel, Charlie, one thing to point to in the NIH area is the protein data bank, for example, which is going to be the subject of a talk at their conference later this afternoon. It's an excellent example of a very high value data collection. In the NASA area, just the Earth observation satellite data, which streams down to white sands and then around through networks, including Internet 2 and others, and are available increasingly, are very important. In the DOE area, what was it? Just the LHC thing is a famous example, right? Rutgers is involved in the CMS project within the Large Hadron Collider world. All of these areas are just increasingly data intensive. So data management is a very big focus of research within the computer science directorates at NSF. It's also the case that both support for data collections themselves, which are most likely to come from the various different discipline directorates at NSF, but also support for improved data tools, database technology, deployed databases, et cetera, will be a very important emphasis within the Office of Cyberinfrastructure. All of these things are very important. Scientists have always wanted to move large files Trump was that in 1985, a large file was a 1 megabyte file, and now a large file is a 1 terabyte file. And so being able to handle, move those files, manage them is increasingly important. And that will be reflected in that cyber infrastructure vision document that's coming out this month, and also in everything that we do.
I'll say again that data-intensive science is very important to DOE and the Office of Science. And I certainly agree with everything that Guy has pointed out. We have done a lot in terms of research and how you move the data, networking research. We had a lot of development in how you manage the data, whether it's moving lots of small files or lots of one big file. A lot of ours is a lot of small files, but that add up to be very large, as in the case with the high-energy physics folks. And we have continuing needs for research in those areas, and anticipate that in our CyBack program, which is about partnerships with the other science offices to advance petascale computing as well as the data-intensive dimension. I'm sure we'll have some important area of research on this particular topic.
One thing I might mention is an indication possibly of things to come within the Terra Grid. During the last year, the Terra Grid had tremendous success with an experimental project, which is to offer a global file system at San Diego Supercomputing Center that now supports 400 terabytes of data that is accessible at very high performance through tools that are very similar to the network file system that many of you are familiar with. And if you have a computation running at NCSA, for example, that wants to read a large data set in San Diego to fill in that global file system, then they can in essence, make full use of the 10 gigabits capacity between NCSA and San Diego and drive those global file systems at very high speed. So very large data sets. In some cases, when those data sets are very, very large, you might want to make use of wide area file systems as one way to access. Just one example of a technology you might see coming up in the next few years.
And we'll probably be working with you on that.
Oh, yes. Oh, yes. Oh, yes.
Definitely.
And NASA is also involved in that wild area file system. We are connecting other teams trying to build that kind of this wide area files across the nation. In terms of when we talk about moving data, really data management is about where do you find the data and how do you move the data, and is there a way to once you locate the data, move the data, or even subsetting or cleaning the data. So we have a lot of research in those areas, and anticipate we will have we will continue to support this kind of research in our access for reason program.
Let me add something else then. So by way of example, then we have the BURN program, and we have CA-BIG, which the BURN and funders of CA-BIG are out there now, providing national and indeed international file sharing and discovery inside a closed world, running on Internet to flow. The speaker's question, I think, addresses something that I think all the funding agencies wrestle with, which is when data is generated by grantees or people working somewhere on research, for the long term, what do you do with it? We wrestle internally and you are outside. And I would add to Lingard's comments also the aspect of curation. It's a very technical area of any component of biomedical research. The ontologies that we're using today, even the keywords that we're using to tag, to associate particular images or data sets, are probably going to be changed in the next 5 years, not the next year, in some minor way, but over time things increase. So you have the other notion of curation, even curating of the discovery components and tools. You can't just stick it onto a disk and leave it. That's what's going to happen. Then there's the notion of provenance of the data. So if I'm a human subject working participating in a clinical trial, I give the researcher permission to use my information on a particular study, and then it's kept. And then 10 years from now, someone wants to do perhaps a longitudinal study using my data, other people's data. The initial permissions were not granted for that, and someone has to come find me to get permission to reuse my information. And lest we forget, and I understand this meeting is about data, but geneticists makes keeping stuff around tissues and animals. We have several 100,000 mouse models for different, which are used for different disease oriented experiments. And a lot of mice. I think you have trouble with this.
Thank you. Do we have, I haven't heard that.
We have a question from King.
I was going to say, yeah, go ahead.
Okay, hold on. Bill?
Just one question. There seems to be a lot of funding and resources being thrown to developing the infrastructure. Will there be, are you aware of equal opportunities for funding or how people want to use the infrastructure that's being developed? That is, people that are doing research. I mean, should they be partnering to help build part of the infrastructure and then also take some of that funding to come up with novel uses, or will be a separate funding cycle to come up with ways to use this really great resource that we're all developing?
I'll see this one first. I'm sorry if I conveyed that impression. There are a couple of examples. So the Lariat program I mentioned as an infrastructure play at the NIH, but it too is driven by biomedical research in 6 northwestern states. The Burn program, cancer, CNV, the National Centers for Biomedical Computing in the NIH roadmap, the informatics aspects of the CTSAs, clinical translational science. These are driven by biomedical research with a cyber infrastructure component. These are by no means free-floating infrastructure plays on their own.
Okay, let me ask one. Moving into a world where cyber infrastructure is increasingly important is it's a new environment for some of our researchers. Can you suggest sort of 1 or 2 technologies that you think are particularly important and that research groups should familiarize themselves with in the short term in order to better work in the new environment?
So the second answer was grants.gov.
In some ways, the answer is discipline-specific. There's a wide variety of different instruments that are capable of generating ever higher data rates, ever higher resolution. So that, for example, the new generation of observation satellites from NASA is giving, at some level, the same old stuff they've been giving for several years, but with much greater accuracy and interest, which is added to the burden of data management and data movement for digesting it almost seems like the right word, and a kind of a scary word. So that in some respects, the most exciting instruments are not the supercomputers and the networks, but the instruments that are causing this avalanche of data, which effectively managed can be of enormous value to discipline scientists from a wide variety of disciplines, but will give people like Charlie and the others at the IT centers around the country a lot of tips through the meantime.
NASA scientists have given a lot of thought on that line. We are generating lots of raw data. Is there a way we can push that, to the instrument, to the satellite? So there's a lot of research on board processing, digesting of the data. So we don't need to store every single bit of the data. Digest the data on board, on the satellite, and we can higher level product. Well, of course, there's a lot of debate on whether or not that's the right way to do it, but we just cannot handle, continue to manage tons of raw data coming from the observation platform.
I'll approach this from a somewhat different view. One of the things that's important to the average professor, scientist sitting at his desk somewhere, is to recognize that the technology is changing and start to be more comfortable using some of these things in your day-to-day operations. Recognizing that there's sometimes you want access to the data, but you have to have some sort of certificate for it, or some sort of authorization. You didn't used to have to do this. So you just need to recognize that this is where things are going, and be willing to change along with the technology.
Okay. We're beginning to get into Manisha's time, but are there any other questions? Okay. Thank you very much to all of our panelists in Washington. The final presentation for the morning is from Manish Parashar. He will talk about some of what's going on at Rutgers that uses cyber infrastructure, and also about how we might develop appropriate cyber infrastructure, develop ways of using it at Rutgers. He's a professor of electrical and computer engineering, also director of